So, we will now solve in this lecture we will solve some problems using smooth chart. So, that whatever is taught in the lectures you grasp, and I also advise that you practice this, because both to do the assignments of this course and doing at the examination will also test your ability to do Smith chart calculations, that will be tested. And also as a professional advice I will give you that if you want to excel in this or a profession, you need to thoroughly understand Smith chart, and this should be a tool like calculator helps and any scientist his studies. If we scientists don't know how to use scientific calculators, then lot of time we waste for doing simple things, which is not our aim. When we do a scientific calculation, our aim is not to do those things that can be done by calculators, but we try to concentrate our efforts in other philosophical things. Similarly, here that in transmission line, if you get bogged down into doing those calculations manually, then lot of time gets wasted. That thing can be much simply done by this tool of Smith chart. So, please practice those things. So, let us see, the first thing that we will do is whatever is showing that plot an impedance of 25 plus J40 ohm on Smith chart. Assume characteristic impedance to be 50 ohm. So, the first thing that you need to do to solve this problem is you normalize, because this impedance Smith chart is a normalized impedance. So, that it is independent of characteristic impedance. So, that is why it has various values which are plotted in normalized A. So, first you normalize the impedance with respect to the characteristic impedance, it is given 50 ohm. So, Z bar will be division by that Z naught. So, you get that R bar is 0.5 and X bar is 0.8. So, then you need to locate the R bar is equal to 0.5 circle. You see in your Smith chart you do actually in the uploaded Smith chart you can take, because there is a software freely available in internet which is called Black Magic Design. I think the people who have done that, they have put, you can download that. Also we have kept sample copies of these things in your extra material portion of this course. So, you see, if you see that thing, you locate that along the real axis the values of the resistances, constant resistance circle values are given. So, there you locate, as we have shown, that you first locate the central portion of the Smith chart, and then you see that since it is R bar is 0.5, it will be to the left of this, and as we have shown in the slide that 0.5 is the circle, you will find out a circle which is passing through 1 0 rightmost point and 0.5. Then you locate what is the constant reactance 0.8 circle. So, X bar is equal to 0.8, you locate an arc. So, you see that on those arcs the values are given, these are given at the inner side of the outermost periphery thing. So, there I am locating 0.8 something here. So, this one is that, and 0.5 I think is this circle, sorry. So, this intersection point somewhere here is our desired that point. So, by this I can locate any impedance if I want to locate on the Smith chart. This is the procedure. The next, let us do this, that instead of impedance, suppose I have an admittance of 0.011 minus j 0.018 mho, plot it. Now, there are two things we can do, either we can plot it on an impedance Smith chart or we can plot it on admittance Smith chart. Now, let us do both the things. So, first let us see the impedance Smith chart thing, then the next problem we will see the same thing, we will plot it in admittance Smith chart. So, again the first step is the normalization. So, you do the normalization with respect to characteristic admittance. Now, for a characteristic impedance given as 50 ohm, so characteristic admittance is 1 by 50 mho. So, you divide the admittance by the characteristic admittance, you get that the normalized characteristic admittance y bar is 0.55 minus j 0.9. So, now you think that in impedance Smith chart, if you want to plot an admittance Smith chart, then you will have to, in your mental plane, you will have to think that constant r bar circle is constant j bar circle and constant x bar circle as constant b bar circle. So, identify these two things. So, now G is equal to 0.55. So, find out, in previous case you have found this. So, now 0.55 circle will be somewhere, I think, here. So, this circle in this chart, this is something 0.55 circle, and then the j minus j 0.9. So, this you will have to locate where is this one will be j 0.9, these are. So, this intersection point is our desired thing. Now, you can see that you could have done another thing also, that if you know okay, so you have located. The second problem is the third problem will be this, do this the same admittance value, but on admittance Smith chart. On admittance Smith chart the labels are different, and the admittance Smith chart, as I have shown, there all the circles are passing through -1 0 point and their values are different, as can be seen here. So, here you see the same point is getting located, 0.55 is here in previous case, or admittance case is here. So, the point came somewhere here, but here you see the point is somewhere here. Now, can anyone tell me that are we making mistake or this is okay? The point is, actually we have already seen that if we reflect any impedance point 180 degree in the Smith chart, we get an admittance point. So, this point, this we got from impedance thing, that if we take a reflection, basically we get the admittance thing. Now, only problem, now out of this which one is easier? Obviously, in admittance, if you want to plot an admittance, you should plot it into admittance graph, admittance Smith chart. If you want to plot impedance, you should plot it in impedance Smith chart. but as I said that sometimes we need to convert an impedance to admittance, because some portion of the circuit is series, some portion is parallel. So, after doing series things we need to convert to that time this problem comes. So, if we are in a impedance thing, then to convert that to admittance we need to take a 180-degree shift. But if all the calculations are in admittances, then the impedance Smith chart you can consider as an admittance Smith chart, there is no problem. So, you can see this. Now, the question of that conversion we are addressing here, that same impedance 25 plus j 40 ohm which I have done in first problem, you convert it to admittance on impedance Smith chart. So, you do as before, plot the normalized admittance. So, you see that we have plotted it in this figure, and this is the point where we have plotted it. Now, to convert it to admittance, what we need to do, this point, from this point we need to connect to the center of the chart, and with this radius and center draw a circle. So, that basically now you know what we are drawing. Basically, we are drawing a constant constant VSWR circle. So, in the transmission line, one of the line impedance is this. Now, if we draw this circle, we are basically moving on the constant VSWR circle. So, now it is easier that this point you just project to the other diametric end, that will be the admittance. So, that is what I said, draw a circle of radius d with origin at 0 0, basically draw a constant VSWR circle, then an admittance will be 180-degree opposite to that, basically a reflection. So, here we are showing that reflection means basically you are at the other end of the diameter. So, now you can read and you see that you are getting the correct value. So, this shows that the procedures, that whether you are in impedance Smith chart using or admittance Smith chart using, you will be able to plot any one correctly. So, these 4 I think examples have shown you that how to plot any impedance or admittance on whatever Smith chart available to you. Now, let us do this, that in a laboratory based experiment, as we said that the VSWR meter has measured VSWR to be 1.5. Plot a constant VSWR circle on the Smith chart. So, whatever discussion we have, we know the step 1, never forget this, that identify the point where R bar is equal to 1.5 circle. Remember, R bar, not VSWR, because there is no VSWR is graduate, the Smith chart is not graduated for VSWR, but it has graduation of R bar. We know that, find first R bar is equal to 1.5 circle, R bar is equal to S, that same circle, and find out where it is cutting the real axis. That is one point of the VSWR circle, the other is origin, the center. So, you know center, you know periphery. So, do the step 2, measure or find the distance, draw a circle of radius d with center. So, you know how to do the constant VSWR circle. So, if you measure something by VSWR meter, you know how to plot it here. Now, let us do this problem. This is about line impedance calculation. if I move along the transmission line, how I can calculate the thing from me. Now, I will also advise you that if any of you are finding Smith chart complicated, please find out you solve this problem analytically, do not do it Smith chart wise. Now, you will understand how much problem you have, and it is much easier to do it at Smith chart. If you understand Smith chart clearly, this is very easy. That is why RF engineers are very passionate about using Smith chart. So, first step is, what is that given, that at this interface I am finding that impedance, line impedance is 100 plus J 40 ohm at 1 gigahertz, let us say, frequency. Now, at Q dashed, which is 4.5 centimeter away from the PP dash point, and it is towards load, find the impedance. So, first thing is this 100 plus J 40 you put, then move towards load that distance, and then you can locate. So, what he has done, first we will have to do that, you normalize, that is always to be done. So, 100 plus J 40 you divide, because it is given that, or he assumed that characteristic, it is written here that characteristic impedance is 50 ohm. So, you divide and it comes that Z bar is equal to 2 plus J 0.8. So, you locate, you can now locate Z bar, that means find the intersection of R bar is equal to 2 circle and X bar is equal to 0.8 arc. So, by that you see that here this is the point which is the Z bar point. Now, here since you are moving along transmission line, we know moving along transmission line means we are on the same VSWR circle. So, you can find out, once you got an impedance, you can always find out that if that impedance is on any transmission line, any impedance, whether it is load impedance, line impedance on transmission line, then you can draw the constant VSWR circle. So, you draw constant VSWR circle, that means this is the center, this is the peripheral point, you complete the circle, and now movement means I am moving on this constant VSWR line. So, step 2, that now you, since the Smith chart markings, movement markings are in terms of lambda. So, you find out that in the problem it was said 4.5 centimeter, but that is how many lambda. So, that you need to convert, as shown here, that lambda for your 1 gigahertz frequency. So, it is 30 centimeter, simple calculation, f by lambda, that 3 into the speed of light, 3 into 10 to the power 8 meter per second is the speed of light by f. So, that is 30 centimeter. So, lambda is 30 centimeter. So, how much is 4.5 in terms of lambda? That is 0.15 lambda. So, that means from the earlier point which you have located, that Z1 point, this one, you will have to now move towards load. See this diagram, you have to move towards load by an amount 0.15 lambda. So, that you look from here, that towards load. So, which side? Towards load means this, in a Smith chart towards load means anti-clockwise. So, you move from this point on this constant VSWR circle anti-clockwise, a distance of 0.15, that means see it from the outward one thing, you move by 0.15, that will take you to this new point. then you connect this, because actually you are moving here, though I am reading from the outer boundary, but on the constant VSWR circle I am moving. So, on constant VSWR circle basically I have come to this Z1 point, I have come to this point, and this value, if I read that what is the resistance value and reactance values, then that I can find, and then my job is to unnormalize it to that. Okay. So, by this we can find the line impedance, and this will be the homework. So, assignment, your assignment will be this. So, you see these assignments. So, by whatever we have taught, you will be able to do this. The first problem, you see that we have given various combinations of this R and B, that means susceptance and resistances, reactances, etc. Some are in series, some are in parallel. So, you will have to find the input impedance. So, what I advise, that since you are asked to find input impedance, you start from the load side. So, there is a load and that is in series with something. So, in the impedance plane you find out those two things, their sums, and then you find out, then there is a parallel circuit. So, you convert yourself to admittance and connect that, find out what is the admittance, then add this admittance, then again convert to impedance, then add that impedance. Like that you can always come here at this point and find out what is the input impedance. So, this will test you whether you have understood this thing, and now you will understand that doing this same thing without Smith chart will be lot of trouble, lot of calculations, but in a Smith chart graphically you can do it very easily if you have understood this. Similarly, the second problem, or the second problem is like our laboratory problem, that in a laboratory we have found the VSWR, and also we have noted that minima shift by certain amount, frequency is given. So, you will have to find the impedance, and also the third problem, you will have to find out what is the input admittance, input impedance and admittance of the transmission line given in figure. We have given the line, we have given the thing, also we have said the line length. So, you can find out from the load, if you are moving along the transmission line, again the same thing, first you locate the load, then you draw the constant VSWR circle, and in that circle you move by the requisite transmission line distance, you will be arriving at a point that is your input impedance. Only thing, that impedance you then need to convert to admittance and give us the answer. So, the assignment will be similar to what we have done. So, I think you will be able to do it. By this we are completing one thing, that you now know Smith chart. The first tool you have known, and we have given example that how Smith chart is used for finding the impedance in laboratory. Also we will see later also in impedance matching and others, in any design of networks we can do that. Later you will see that if I want to study design an amplifier, and I want to study whether that amplifier is stable or not, Then also this Smith chart is helpful if you want to carry out that whether it is having the noise figure is acceptable to you or not, whether its gain is what you desired or not, whether from that amplifier you are getting good gain, whether you are having its noise kept at a minimum. So, all those designs that time you require to use Smith chart heavily, you understand. So, that Smith chart is a tool which will help you to attempt these designs, that how to design an amplifier when a gain is specified. What is the best possible gain I can get from that amplifier under given impedance a thing. Given the load condition, can we do anything to achieve extract the maximum gain from that? Can we design it for a given specified noise figure value, that my noise figure should not go there? Those are required for low noise amplifier designs. Then, so all these circuitry where there are oscillations possible, you can do that. Then you can design for oscillator design also, which is a design of an active device. Then you can take this Smith chart, though we have introduced Smith chart for passive devices, that standard Smith chart, with some conversion you can make it for active devices and you can do that. That is another technique, but the same Smith chart fundamentals will be needed there to attempt those oscillators design, what is its stability, which zones are under which impedance conditions you are stable, etc. All that your Smith chart will be doing. So, we have completed in this whole module that the Smith chart as a tool has been introduced. So, please go through the assignments, try solve those assignments, submit, and if you can have these assignments, then it will give you confidence that you have learned something how to use this tool Smith chart as an RF engineer. Okay.